morning, everybody, and welcome to another episode of Environmental Social Justice. I'm your host, Wendy Nystrom, and today we have our returning guest, Tanya Chandler. She is the president of BioLargo's Equipment Solutions and Technology. Welcome back, Tanya.
Thanks for having me.
Anytime. So last time you were here was about a year ago when we talked about PFAS and the dangers of it and things going on with that. For those who may not fully understand what PFAS is or what it stands for, would you mind giving just a brief history of that?
Sure. So PFAS is actually polyfluorinated alkaline compounds. So what PFAS is the substances that make things grease-proof. They make things waterproof. They help things be non-stick. They're used in manufacturing. They're used in a lot of our modern day conveniences. So when we talk about the history of PFAS and how long they've been around, the first PFAS compound was actually developed in 1938 by accident. It was a laboratory test gone bad. But when they started to look at what had happened in the reaction chamber that they had used, they found this kind of soapy white substance. They went, what is this? So they started testing it and they found out it had these amazing properties because it didn't react with anything. It didn't burn easily. It allowed things to slide, made things waterproof. It was amazing.
Yeah.
So instead of just throwing it away, they're like, what can we do with this? Well, right around the time that all of this happened is the time that we were creating the atomic bomb. So everybody's probably seen the movie Oppenheimer and everything. The reason that that was able to happen was because of PFAS. The Teflon compound was the only thing that would hold up to the seals and that they could line the insides with so that it didn't react with the plutonium and the uranium. So for up until about 1945, it was only a military product. As we started hitting the end of the war and the military wasn't going to have this vast need for it anymore, they started wondering what else could we do with this product. And you started seeing things like fishing line. So you got Teflon fishing line. You started seeing nonstick cookware. The funny thing is that if you take the first PFAS compound being PTFE, it's stable. Really doesn't do anything. It doesn't react with anything, but you can't get it to do anything either. So you can't get it to adhere to things or anything like that until you add a surfactant, enter C8, or what we know as PFOA.
Gotcha.
So they mix those two compounds together to get it to actually be able to be used in other products. So that's where we've come now in 1946, 1947, when we started talking about things like nonstick cookware and everything. From that time forward, you're starting to see PFAS-laden materials get put into landfills. We've been using them, but they are used in some of the major advancements. So things like, okay, everybody knows the issues we're having with lithium-ion batteries.
Yes.
Well, before we had fires from lithium-ion batteries that wouldn't go out, we had problems on ships where jet fuel would actually spill and start on fire, and they couldn't get it to be put out. So in the 60s, the military worked with companies like 3M and DuPont to create a better firefighting solution. Enter AFFF fire foam that was a combination of PFOA and in the process PFOS, among other things, that would actually smother the fire. So it depletes it of oxygen, it doesn't evaporate, but it doesn't allow it to reignite. So you're smothering it.
Yeah. And washing off the decks into the water, but that's another thing.
In about 2015, we stopped using PFOS and PFOA in firefighting foam, and we moved to quote unquote short chain PFAS, the smaller chains that we talk about in everything that we're doing. And so in that, we actually moved to PFHXS and PFHXA.
Okay.
And those are the new class of firefighting foam, except in all of the stuff that we're starting to see, like the initial RCRA language that came out. PFHXS and PFHXA are included in that language. So we know that they're not much better. The short chains aren't much better than the long chains of PFOS and PFOA, but we're still at a crossroads with certain things. We'll
Yeah.
never be able to get rid of them completely because the military uses them in our warheads. The military uses that firefighting, and they need to. It's
Yeah.
the only thing that will put out the jet fuel fires. It's the only thing that will put out your lithium ion battery fires right now.
Yeah.
So we can't ban it completely. It's what it's the reason you have contact lenses. It's the reason that you have blow mold factories, so your bottles, like your laundry detergent bottles and things like that. It's what keeps the nozzles from clogging. It's what makes plastic bend. So it's not just the waterproof and the grease-proof aspects that we're looking at. It's a lot of the manufacturing advancements.
Yeah.
You microchips without it.
So this is basically something used in just about everything imaginable. And the
Yes.
reason it's now a contaminant of concern, so to speak, is because it has, they call it a forever chemical because as it gets into our systems, into our bodies, it does not break down. It
No,
actually builds up.
it lodges in a proteins in our, or it connects to the proteins in our blood, lodges
Hmm.
in our liver. There is some studies that say if you give blood, it will
Yeah.
follow the blood out. And then you're
Awesome.
making news, but we're exposed to so much of it on a daily basis because it's in the air, it's in our rainwater.
It's in
It's
everything.
not just coming from the products that we use, it's now lodged itself in our environment. And it's following the evaporation cycles, it's following the wind.
Oh, yeah.
It's why you're finding it, 3 feet deep in the Arctic, you're finding it in the rainforest. They found it on Mount Everest.
Yeah. And I mean, so here we have this dichotomy. We have this great product that is used in everything. Non-stick contact lenses. I wear contact lenses. That was a new one for me right here, folks. I did not know about the contact lens sides. All of it's, we've already got it in our systems, but it is a known carcinogen. It is bad for us. But we have to have it because, as you said, it is the only thing that will put out jet fuel fire or lithium ion battery fires. Nothing else will smother those fires. So it's kind of a necessary thing that we have to deal with. So it's not going to be banned, as you said.
No, it's not going to be banned. You will see it as some states have gone, no, intentionally added PFAS in products.
Okay.
But you will never see it. The military will always use it. The medical industry will always use it because it has allowed them to do things like heart transplants or valve transplants. When things get put into your body, you need them to not react and not break down.
Valid point. Valid point. So now we have
So
to deal with our contamination and pollution issue.
now we have to break the cycle.
Yes.
So it's been in our environment. So now we have to start removing it and we have to watch how we're disposing of it. So recently, we're starting to see some of the new regulations come out. We're seeing the first language for RCRA, which has a ways to go yet, obviously, before it's law. That's just how all of the process works.
And just so
But
people know, RCRA is the Resource Conservation Recovery Act. It's a federal law. Just throwing that in there.
yes, it governs disposal of hazardous materials.
Yes.
It is so they're looking at it, adding all of those to Appendix 8. Appendix 8 is that it's a known toxic substance.
Yeah.
Doesn't make it full hazardous waste yet, but it's a known toxic substance. It has some kind of toxicity that we can prove. It's for governing of open sites and disposal. We're also waiting on language to come out for something called CERCLA, which people would know better as Superfund. This covers closed sites.
Yeah.
Okay. So this covers sites like closed landfills, where we're going after the cost of cleanup after a site has been deemed hazardous, or containing hazardous materials. These two things are a backbone for disposal.
Yeah.
A guidance was just put out by the EPA that says if you're going to dispose of PFAS laden material, whether it be leachate from a landfill, whether it be ion exchange resin that's spent, carbon that's spent, it should be treated as RCRA. If you're going to put it into a landfill, it should go to a Class C or a Class D. If you're going to do deep well injection, you need to be dealing with a handler that has a hazardous waste deep well injector system. If you're going to incinerate it, it should be incinerated at hazardous waste temperatures by somebody who's used to dealing with hazardous waste.
Okay.
So what this means is they're recognizing already, the EPA is recognizing that we need to break the cycle.
Yeah.
Now, we just saw the drinking water standard come out, which is what we're really here to talk about.
Yes.
And the drinking water standard came out, and it was somewhat expected, but also a little bit of a shock. So everybody expected PFOS and PFOA to come out at 4 parts per trillion. Now, to give people an idea of what 4 parts per trillion looks like, take the Great Salt Lake in Utah and drop 4 drops of water in it. That is 4 parts per trillion.
That's a very tiny, tiny amount.
So PFOA, PFOS, 4 parts per trillion. Now, they set 2 levels in this rule that came out. They set a maximum contaminant level, which is the enforceable level. They also set a maximum contaminant level goal, where this is where we'd like you to be.
Okay.
Maximum contaminant level goal was 0.
Nearly impossible to do, but okay.
Yes. So that's not, the 0 is not enforceable, but the 4 parts per trillion is. And the way that the guidance is written, they're going to give everybody until 2029, or the way the rule is written, to 2029 to be at that level. The reason that they're doing that is just naturally in the municipal funding cycles.
Okay.
It's going to take that long to get everybody's equipment and projects funded.
Oh, yeah.
Get the equipment ordered and have enough equipment to go around. Really, I mean, when you talk about manufacturing.
Yeah.
So they started with the 2 majors there at the really low level. Then they went to the small chain PFAS and some other long chains that aren't as known. So we've got Gen X, and they set that one at 10. Okay. We've got PFNA, which is actually a long chain PFAS, but they set that one at 10.
Okay.
They've got PFHXS, which they set at 10.
Okay.
There's another PFAS in there that people don't realize, because at the bottom, there's a hazard index. And the hazard index is, you take a 4-quarter running average. So go back 4 quarters, average out your numbers, and then divide them by the formula. So if you're looking at this, it's Gen X divided by, I believe it's 10. And then you'll get a ratio. And then you'll get PFHXS divided by, I believe it's 10 with the ratio. And then PFNA divided by 9. But the 4th one that's thrown in there is PFBS. That's divided by 2,000. You add those numbers up and you get to a number at the end. You add those ratios, you'll get to a number. Yeah. If that number is greater than 1, you have to treat. If it's less than 1, you're okay. The reason that they do this is they're looking at they want to set the hard numbers, but they also want to say if you're exposed to these 4 together, then we need to have you under this. And that's taking into account that 20% of your exposure to these compounds is going to be through your drinking water. The rest is going to be in the environment, in the products you use, etc.
Yeah.
Now, having said all this, 4 parts per trillion,
Yep.
10 parts per trillion on these, not always easy to get to with traditional treatment.
Not at all, because again, even though this had been around a long time, not many people have paid attention to it until recently when the lawsuits went flying. And no one really knows how to effectively treat this except you guys.
I don't know if I'd go that far.
Oh, I will.
But what happens is traditional treatments, and what's identified as traditional treatments are granular activated carbon, anion exchange, and then you also have RO. Those are considered the traditional treatments. Reverse osmosis.
Okay, just so people
They
know.
all have challenges when it comes to treatment. So granular activated carbon is very effective on PFOS and PFOA. Very effective. It's going to remove the long chain PFAS, right? But it's going to struggle with things like what they call channeling, where water takes the path of least resistance.
Mm-hmm.
So you get what the channels of untreated water coming through your system after a certain amount of time. The other thing that you're going to run into is if you've got groundwater and you've got, certain other constituents in it, it could use up the carbon faster than the PFAS.
Yeah.
You've got, in order to get the contact time that you need for PFAS removal, you're looking at 10 to 13 minutes. And they recommend basically a double-sized system because they want what's called lead lag. So you go through one bed, and then that same bed water goes through another bed. So you're doubling the size of your system.
That's a lot of space, too.
It's a lot of space. It's a lot of carbon. 1 million gallons a day is around 160,000 pounds of carbon.
Yeah.
Dry weight.
Yeah. Oh, yeah, that's a lot.
So when it comes to disposal once a year or more, you're looking at 160,000 pounds plus the weight of water to transport and dispose of. And with the new guidances, you're either disposing it at a hazardous waste landfill, if they'll take it.
Yep.
Or you're incinerating it. And with the new rules, you are going to see disposal costs skyrocket.
I'm surprised they would incinerate it. Wouldn't that just put it in the atmosphere?
And actually, if you read the guidance, it actually says that we can't guarantee that you're going to qualify with clean air standards later. But there's only one place in the country that's incinerating it and doing a lot of stack testing to try and combat that.
Okay.
So there is one, but their capacity is limited as well.
One would think. I mean, you don't want to take it out of your groundwater and out of your landfills and out of the soils and put it in the atmosphere. It just
exactly break the cycle.
Yeah, it's counterproductive of what we're trying to do, and that's a ton of waste generated. That really is.
It really is. And so the same thing with ion exchange. Now, ion exchange, you have to worry about a couple of things. You have to make sure, again, you don't have competing ions because you're using anion exchange. So things like nitrate that's common in groundwater, arsenic that's common in groundwater, silica that's common in groundwater are all going to use up that resin. There is some people that say there's PFAS selective resin, but we'll see. And again, the short chains are going to go right through both of these methods. They don't adhere well, or if they do, the long chains will come along and push them off and throw them back into the water stream. So there's challenges there, but like I said, for long chain, it works for those PFOS and PFOS, but can they stay consistent without having to change that carbon out every 6 months or that ion exchange resin out every 6 months because of that channeling, because of the interfering ions? So there's a lot of unknowns, and with anything, systems are unique. So it's what's going to work best for your system. There's no black box to all of this.
No, every environment is going to be a little bit different of what is actually already in your soils and groundwater that, as you said, will adhere to the ions.
Exactly. So then you've got reverse osmosis, which is a very effective way to remove both the long chains and the short chains, but you have a concentrated stream of PFAS now that you have to deal with. Most places don't know how to deal with that. You can't put it right down to your drain, or you're going to end up having to deal with PFAS at your wastewater plant.
Exactly.
So enter
It's
somebody
the can
like
down the road, basically.
yeah. So enter somebody like BioLargo. We can treat that concentrated stream. Our system is an aqueous electrostatic concentration unit, otherwise known as AEC. Basically, we use the polarity of the PFAS against itself. We create a very strong electrolytic field across a chambered unit. Water comes in. We've got membranes that separate our chambers. The PFAS goes towards the anion. We capture it onto a membrane. That membrane, it's not coming off of it. That membrane seals it, basically. I mean, it sticks to it like flypaper. So we can backwash our unit. We can clean our unit. It doesn't come back off.
Awesome.
We are able to get the long chains. We are able to get the short chains very effectively, and they stick as well. We've actually been very effective at getting things like PFBA and PFBS, which go right through traditional treatment, except for RO. Goes right through the carbon and the ion exchange. We've been able to remove those.
Okay.
Very effectively, down to non-detect.
Really?
Yes. So we've been able to get all of the PFAS we've tested down to non-detect.
That is impressive to get it down to that. That's very different. Yeah.
When our modules are ready, when they can't take any more PFAS, or they're to the time of maintenance, we will actually take the modules back. We will actually take the membranes out. We will load it with new membranes. It can now go back into the field. All we have left for disposal is that membrane.
What do you do with that membrane?
So then we take and we strip the active area off of it, and we run it through a destruction process that takes it all the way down to mineralization. So we actually have our own destruction process that we've now patented, that we can actually mineralize it so it's now down to inert salts. What that means is on site, if you would go apples to apples, spent membrane to spent GAC, we produce 1/42,000th the waste of a carbon system on site. Then we take that
granulated activated carbon, just so people know.
Yeah. So then we take that waste and we dispose of it. We take the RCRA liability on us.
Oh, that's important. Yeah.
We also offer a process guarantee with that system. So we'll offer you a maintenance contract. That maintenance contract will ensure that you're going to meet your PFAS levels. You're going to meet the regulations for your state, because remember, this is federal levels, but each state is different. And states like California and Massachusetts have already started to work on levels that are lower than the federal levels.
It's good to know, actually.
So we'll guarantee that you're going to meet your levels. And then we will take the disposal on us. And for the life of that maintenance contract,
that's kind of, I really want to hone in on the fact you're taking the liability of that disposal. That's a very large liability to take on, that you are relieving your clients of, because disposal, as you know, when we talked about the beginning with these new laws coming out with RCRA, all landfills and all wastewater treatment areas are going to have to be reopened, because these are contamination levels that we never had before. So now you thought your site was closed, not the case anymore. It will get reopened. So now you have to go back to it. So now you're taking on that responsibility of, we're going to fix it, and we will continue to fix it.
Absolutely.
Not many people do that. That is a service most people don't offer.
Well, we just feel our guys have been dealing with the hazardous waste laws and regulations for 30 years. We're probably better equipped, especially if you're a small town.
Yeah.
We're better equipped to deal with it.
Yeah. No, without a doubt. I mean, most people, this is a new contaminant to them. Most people hadn't heard of it 5 years ago, 6 years ago. I mean, I only first came across PFAS probably 12 years ago. And when I first, some of my science buddies were talking about it, and I'm like, what's the big deal? What is this? Why do we care so much? And they said, it's going to be the new asbestos. And I'm like, oh, you're just being crazy. You're talking crazy. Nothing can be as bad as asbestos. Here we are.
But think about how long now it's taken them. They just finally regulated the last asbestos.
Yeah.
I mean, we're going to be dealing. This is just the tip of the iceberg. That's the thing that everybody needs to understand. These drinking water laws are not the only ones coming. These are the first 6. There's more to follow this. So when you really start looking at this, we need to look to innovative technologies rather than traditional technologies, because the farther we go into this, the more short chains are going to be regulated.
Oh, yes.
So we're here not just, so our company is, an equipment and solutions company. So what that means is that we try and help our client. We can just sell equipment. If somebody, is working with an engineering firm and they like our solution, we'll sell it to them. And, but we're also here to be consultants. We're also here to help our clients from start to finish to make sure that they're selecting the best technology for them, to make sure that they've got the education that they need, to guide them in the right direction, and not because we don't believe in putting a square peg in a round hole. If our technology is not the correct one for them due to something in the water or whatever, we're going to tell them, and then we're going to help them find the right solution.
Which is where your expertise does come into play, because this is a very, very specialized industry. There are not a whole lot of people out there that have the knowledge that you've got.
It really is specialized, and sometimes with with the makeup of the PFAS in the water, you got to look outside the box.
Oh yeah.
Our system has been successful with drinking water and groundwater. It's been successful with water that is like right outside of an Air Force base.
Interesting.
That is high in volatile organics. We've been successful with leachate now. We've been successful with wastewater. We've got all these successful tests, but we're still not going to tell you that it's fit for every water source.
Yeah.
It's a matter of testing. And we offer that to our customer. We will offer the ability to test a small amount of their water and show them exactly what this system's going to do.
And when you talk about wastewater, one of the most important things we're seeing now, especially in the West Coast, is the whole water recycling. It's not just about conservation anymore with our droughts and everything happening. It is recycling. And we need to make sure that the water we're putting back into our potable or drinkable water scenario is something that won't hurt you. So that is also very, very important to have on hand.
Absolutely, especially with California approving the direct reuse.
Yeah, it's still being worked on. Hopefully, they call it the purple pipe. And hopefully we will get that reuse up and running, because the droughts are, right now we've had a couple wet winters. That's unusual. And we are just going to see the droughts get worse and worse the entire western side. I'm not just talking California. I'm talking all the way up to Portland, Oregon is seeing droughts. Whoever thought that Seattle would experience droughts?
We had a very dry summer and winter, even in Wisconsin.
Oh, and I'm from the Midwest. When I grew up there was a lot of water in the Midwest, and the fact that we had dry conditions, we're seeing our new normal, and we need to adapt very, very quickly to this, because we can. Mexico City is apparently running out of water. Who knew?
The good thing with all of this is that innovation is taking off. That's, as long as we are open to innovative technologies, as long as we're supporting that innovation, the reality is that we have to look for innovation, because you look at the number of sites that are impacted with PFAS across the US.
Oh yeah.
Take out the rest of the world, which is also, working on regulating this and treating this. Just look at the US.
Mm-hmm.
And if you take that number of sites and would try and put just on the drinking water systems alone, try and put carbon, there's not enough carbon.
No, there's not. As you said, with the dry weight being 160,000 pounds, I think you said.
Yeah. So when you're looking at all of this, you have to look towards innovation. because we have to get away from, there's still going to be the place for traditional carbon treatment. It's still a great technology. There's
Absolutely.
still going to be the place for ion exchange. But there's also room for that innovation to make the advancements that we need, both on the drinking water side, the wastewater side, the destruction. Because as you get to the wastewater and you get to the leachate that's expected here within the next year,
Yeah.
we're supposed to start seeing these regulations come forward. Traditional treatments don't work well on those.
No, they don't. They weren't designed for this. This is something
No.
new, and we need the innovation. So going back, I've got some statistics that I do want to share on the AEC. It removes more than 99% of the PFAS from water in a continuous flow. The energy costs were as low as 30 cents per 1,000 gallons. That's pretty remarkable. People probably don't realize the true cost of how much, the true cost of pump and treat and the carbon activated. It's expensive. There's a lot of energy being used. So that's a really good affordable per gallon basis. And you're energy efficient. And then the waste material at the end of the day being so much less with that stripped away membrane. That is very important that people think about, because when you have these large carbon granulated or activated carbon, 160,000 pounds, I think is what you said, dry weight. Then you add the water weight. Not only is that bulk, but that's weight for transport to a facility that may or may not take it. And when I was working in the field as a geologist, there were sometimes we had to take things 5 or 6 states away just because they were the only ones that would take the waste.
I talked to somebody the other day, a system that's in Florida.
There you go.
And they're trucking their waste to Utah.
Yeah. When I was in Massachusetts, we trucked waste to Detroit.
Yeah. Now think about that for a minute and think about the number of trucks that it'll take if you've got 160,000 pounds of carbon. The same system for me, I would have about the size of maybe a coffee mug.
Brilliant.
To dispose of.
Absolutely brilliant. That's a great analogy. That puts things into perspective, because we do need that waste to be minimized. And people, they don't, like, oh, we're just trucking it. That's a whole bunch of greenhouse gases and pollution being pumped in the air just to get it from point A to point B. So we're kind of negating what we're working on with trying to remove overall contamination and pollution from our environment.
They are trying to do things like, can we regenerate ion exchange? Can we recharge carbon? I don't want to negate that, but what they're also saying is, what happens when we recharge the carbon? Where's the PFAS going? Are you going to create a concentrated stream? Is it going up into the air? What's happening with that?
Yeah.
Same thing with ion exchange resin. They talk about regenerating the ion exchange resin, but they're doing it. They can't do it with brine alone.
Yeah.
They need to add an alcohol to it. Well, that can denature the resin and reduce the capacity of the resin. So these are things that if you go out and read the disposal guidance that the EPA put out, they talk about. So they talk about not only how you should deal with this, but also the challenges that are associated with some of both the traditional treatment and where innovation is going.
We have to start thinking full system, full cycle, whatever people want to call it. We can't just say, oh, well, we'll do this. You have to think about, where is that going? If you're reactivating the carbon, where is it going? Where are you stripping it from or moving it? You have to think about these things in its entirety, which is what you guys have done. The small amount of waste that you're generating, the energy efficiency of the system, that's really remarkable. And yes, I'm a huge fan of what you guys do, so I'm biased. I'm going to admit it.
I'm glad you are.
So Tanya, how do people find you if they want to get in touch with BioLargo? What would be the best way to get in touch and talk to you guys about this?
So as we're talking about our PFAS, we created a website that is easy to remember. It's just bestpfastreatment.com.
Brilliant. Because that's what someone's going to Google, bestpfastreatment.com.
What's really fun is, if you think about it, BioLargo equipment, solutions, and technology. Best.
Oh, that's good. You guys, you're full thinkers here. You think it all the way through.
So bestpfastreatment.com, and there is a contact icon on there that they can send us an email.
I love it. That's so great. And you're also on LinkedIn, so you guys are, easily found on LinkedIn. That's how I found you guys and connected with you guys so long ago now. Feels like eons. But you're doing awesome work. I'm so glad you came back to give us an update, because this is a problem that's not going away, and BioLargo is actually ahead of the curve in trying to figure out the solution.
Well, we like to take on big challenges.
Oh yeah, you've taken on the Herculean challenge right here. So guys, thank you so much, Tanya, for your time. This has been extremely educational. I love the work that you guys are doing and trying to do things better, which is very important. So thank you for your time today.
Thank you.
Anytime. I'm Wendy Nystrom, your host with Environmental Social Justice. Please check out Tanya Chandler. Please check out BioLargo. Please check out their PFAS treatment. This is very important stuff. We got to clean up the water and the soils. We'll talk to you later. Bye.